We can start the second day of the conference. The organizers received complaints about the weather. These complaints have been successfully dealt with. And I'm presenting the first speaker this morning. Will Sabin will talk about a conjecture of Poonen and Volok, part 1, probabilistic models for counting rational points on random Fano hypersurfaces.
Thank you. Thanks to the organizers for inviting me to speak. So this will be a talk all on joint work with Tim Browning and Pierre Lebudac. And so Pierre will speak next. Tim isn't speaking, I guess, because he's an organizer, and also 3 talks on this I think would be a little bit excessive. So we're going to let V be a hypersurface of degree d in Pn over the rationals. We can let Fv be the associated polynomial of degree d. And so if we demand that this has integer coefficients and no common factors, the polynomial will be unique up to sign, and then I'll ignore that, and everything I do will be invariant under sign. So we're going to define the height of the hypersurface V to be the norm of F using kind of the obvious Euclidean norm on the space of polynomials. And we're going to work not just with one hypersurface, but with the set of all hypersurfaces of a given, let V dn and d of B be the set of all V of degree d and Pn with height at most b. And so, well, or sorry, it should be an A. Okay, gotta get a little. That would be very bad if that was a letter B. The whole theorem would be false. So we're going to be interested in understanding what properties of a hypersurface might hold on average over this family, even if we can't prove them for an individual hypersurface. So the main thing will be the Hasse principle, which we've already discussed many times in this conference. So we say that V fails the Hasse principle if it has p-adic points for all p. It's non-empty. V of r is non-empty, but the rational points are empty. So the conjecture of Poonen and Volok, that will be the subject of this talk, the conjecture is that if n is greater than or equal to d, which is the Fano case, the density of hypersurfaces that fail the Hasse principle is 0. So more formally, the limit as A goes to infinity of the cardinality of the set of V in V dn. Okay. Thank you. V dn of A such that V fails the Hasse principle. Okay, remember to put the absolute value divided by the cardinality of V dn of A should equal 0. So some motivation for this conjecture is there's the conjecture of Colliot-Phelan that the Brouwer-Menin is the only obstruction to the Hasse principle for smooth Fano manifolds. And then there's a theorem that the Brouwer-Menin obstruction vanishes for hypersurfaces if n is greater than 3, I think. So for smooth hypersurfaces, which is a density 1 set of hypersurfaces, as long as n is greater than or equal to d, they're smooth Fano, which means we expect the Brouwer-Menin obstruction is the only obstruction, and the Brouwer-Menin obstruction is no obstruction at all. So there's kind of a motivation which suggests that this should hold not just for density 1 set, but for all hypersurfaces, all smooth hypersurfaces. But in fact, we don't know how to prove for all hypersurfaces, but we do essentially know how to prove this for density 1 set. So the theorem of the 3 authors is the conjecture holds if n greater or equal to d plus 2. So an only slightly weaker hypothesis is needed, and then the conjecture holds. So some cases of this conjecture were already known. I don't think most of them were intentionally working specifically on this conjecture. So one that almost everyone should know, the case d is equal to 2, the Hasse principle always holds, and this is due to Hasse-Minkowski. Similarly, if d is if n is greater than something like d minus 1 times 2 to the d minus 1, then the Hasse principle always holds, which is due to Birch. And if n is equal to 3, d is equal to 3, the Hasse principle holds as soon as the Galois group of the 27 lines is large enough, and that's due to Swinnerton-Dyer, and then the Galois group is large enough with density 1 by Hilbert irreducibility. And so those are the only cases that are known as such, and these are all really results about a single hypersurface rather than statistical results. But in the world of statistics, there are some similar things. Oh, maybe so you think this is only for diagonal? Okay. Well, another result, which is for diagonal hypersurfaces, is the result of Bruden and Dietmann. Which is for a random diagonal hypersurface with n greater than 3d. And then, so for n greater than d, we expect the conjecture is false, or n less than d. And one example where we know this is the case of cubic curves, where Mandel-Bargava computed, actually exactly computed the percentage that fails the Hasse principle, and it's some positive proportion. Yeah, thanks for the correction. The motivation, I should say, for this conjecture is that in the same paper, Koenen and Volok, where they make this conjecture, they calculate the fraction of hypersurfaces V that are locally soluble, or they show that it's equal to the product of the local terms that you would expect. So knowing this conjecture will tell us the density that have a rational point and give it some product of local densities.
Well, isn't it the case that the case of plane cubics actually get a positive proportion failing that?
Yeah, I said that, but I meant to write, yes, it's a negative result. Yes, I said that with my words. I should have written that on the board. Yeah, so I just put it on there because it's one of the only cases that's known. All right, let's see if I learn how to use the board. Actually, maybe we should, if I send this one up like a few inches, it'll be. Wait, this goes down. Okay, I'm not so good at this yet. So the idea for trying to attack this conjecture rather than the statement for all smooth hypersurfaces is to use statistical properties of the family of hypersurfaces. So the theory behind the proof we must use invariant. Use some invariant that is better behaved on average over hypersurfaces than for an individual hypersurface. Or than for an arbitrary individual V. And so the invariant, as I think is common in statistical, I don't know. Well, the invariant is the number of points of small height. For a vector x in Zn plus 1, which is primitive, which corresponds to some point x in the rational points of Q, we'll define the height of x in the canonical anti-canonical way, which is the norm of the vector x to the n plus 1 minus d. And so we'll use Pn? Oh yeah, Pn, yeah. Use the invariant nv of b, which is the number of x in v of q with the height of x. So that's at most b. And then we will study the statistics NV of B over V dn of A. And when we're studying statistics, so this is an invariant. We can think of this as a probability space if you're inclined to think probabilistically. And we'll want to study the distribution of this random variable. And when we're studying statistics of something like this, I think it's helpful to keep in mind a heuristic for what you expect the statistics to look like, a random model. So I'll give a heuristic, which I think is accurate. And I think you can check that all the results we'll prove will be consistent with this heuristic, which is that NV of B is a Poisson random variable with mean B over A. So the mean of times prod P mu V of QP, where mu of V of QP, mu of V of R are independent. So the Poisson, so I'm saying that basically a way to generate a random hypersurface, the rational, or the point of count, the count of points on a rational random hypersurface, is you first generate for each p a random, like p-adic hypersurface and take the measure of points. And then for R, you generate a random real hypersurface and take the measure. And then you multiply them together with B over A, and then you plug that into the Poisson distribution. And that tells you how many rational points there are. Philosophically, what this is saying is the Poisson distribution is the distribution of independent low probability events, many independent low probability events. And then rational points are indeed low probability events, and they should be very close to independent. But they're not completely independent. And the failure of independence is going to come from these local densities. That if there's many p-adic points, there's likely to be more rational points. And so this term is the asymptotic, or this is from Monet's conjecture with the pair explicit constant. And the dividing by A. So the reason that we divide by A here is sort of most clear if you just think about the simplest heuristic for the number of rational points, which is that the probability that any x satisfies the equation is like 1 over the average size of f of x. And then the average size is proportional to A, because the coefficients are of size A. So using this heuristic, you can check some different strategies for proving this, and you can check some things that won't work. So for instance, one very general method for showing things are non-zero on average is to compute some moments, like to compute the first moment and the second moment of the distribution, and to derive from that some lower bound for the number of non-zero number of non-zero values, which would be the number of hypersurfaces that have a rational point. So this would work. This will give us some lower bound, but for the number of hypersurfaces that have a rational point. But it won't give us the lower bound that we want, because basically the variance of these distributions is too large. It would only really work if these distributions were some very strange thing that was 0 or 1 100% of the time. Yeah.
Are you thinking how large are you thinking about A and B relative to being
So I think that this heuristic should hold for like very wide ranges of A and B, but we'll only be able to prove stuff when A and B are within a certain power of each other. For most of what occurs in my talk, it's actually not really going to matter how A and B are relative to each other, so you have to wait to Pierre's talk to hear about the relationship between A and B. So we must incorporate the local measures, mu of v of qp into our talk, into our proof. Or it's very unlikely that our lower bound will exactly match this kind of predicted value, which depends on these local densities. Our lower bound for the number with rational points should match the number that are locally soluble. So we need to incorporate the local hypersurface into our proof. First idea of how we could do that is we could study. We could show that nv of b minus the predicted value is small on average, and show that the b over a, mu v of r, prod p mu v of qp, is large on average. So if we show that the predicted number of points is large, and the error between the actual number of points and the predicted number of points is small, then we'd certainly be in a good shape. And you can check, if you believe this heuristic, that statements of this form should be true. But the problem is it's too hard to do analysis with these terms mu of v of r and mu of v of qp. Because they could vary, they could depend on the congruence class modulo many different primes p all at once. And so it would be harder to do the analytic steps of the argument with that. So what we'll do instead, we work with an approximation. So rather than calculate the local measure exactly and use that to approximate the number of points in a ball, we're going to approximate this local measure, approximate this product of local densities, and we'll use that to approximate the number of rational points. So our approximation will involve two additional parameters, alpha and w. And then alpha will tell us how careful our approximation will be at the Archimedean prime, and W will tell us how careful it will be at the non-Archimedean prime. So this will be alpha is a positive real, and W is a natural number. All right, actually, look at what I wrote down so I don't get it wrong. So we're going to, instead of counting rational points, we're going to count points that satisfy the equation mod W, and for which the value of the polynomial is small. So this is the expected average size of the polynomial, and we want to make it an approximate solution, so its value will be alpha times smaller than the approximate size. And then we're going to sum alpha W divided by norm F V norm X to the D. And the reason that we sum this term is if f of x is 0 mod W, f of x is bounded by this length, the probability f of x as an integer should be equal to the number of integers mod 1 over the number of integers mod W in this interval. So the probability that x is an integer should be 1 over norm of f times norm of x to the D divided by alpha times W. So this is like the probability that x is an integer.
Probability that f vanishes.
Yeah, probability that f of x is equal to 0, morally. Yeah, sorry, the probability that it's 0 because we know it's a multiple of W in this range that f vanishes. And then so we have a few different parameters going on right now. So I'll explain them. We have parameters. A, which is going to be going to infinity. B will have to take to go to infinity with A. W and alpha will go to infinity. Because we want our approximation to get better and better over time, that will require W and alpha to go to infinity. And we'll also have a parameter eta going to 0. And so our proof is going to follow from two propositions. The first one is we'll be able to choose A or B, W, alpha, eta, appropriate functions of B. Such that the difference between the predicted value and the actual value is usually small. So that we look at NV of B minus NV of B alpha W. And we want to know this is at most eta times its expected value B over A.
Appropriate functions of A? B, W, alpha, eta.
Wait. Oh, yes.
No, at the end you wrote appropriate functions of B. That's
Oh,
all.
yes, sorry. Okay, yes. Okay. Got it. Sorry. And so we want to know that the number of V in VDN of A satisfying this condition divided by the number of V in VDN of A, or cardinality of VDN of A, that this should go to 0 as a goes to infinity. Yeah, so we have an approximation. Yeah. Let's make this, put a greater sign and sign there. How about that? And have it go to 0. Yeah, so we have an approximation, and we want to know that usually the error in this approximation is not too large. And so, in fact, we should conjecture that as b goes to infinity, this is true for all hypersurfaces, for all eta. But that's too hard. But on average, it should be true. And we'll show it's true for b and a in some range relative to each other. And so, as mentioned, if you want to find out what range is, you'll have to wait. So the second thing, it will be a result about the approximation, the approximate value only. So it's kind of a local result. So it's a proposition 2, assuming A and B are sufficiently large, relative to the other parameters, eta, w, and alpha. Then the limit as a goes to infinity, and I'll give to the set. So the limit as a goes to infinity of the probability that the approximation to the right number of rational points is small, that limit should also be 0. Yeah, so here it's important that eta is going to be going to 0. So the proof of the theorem, assuming the propositions. Oh, wait, very important for this proposition. And I need to put, and the V of QP is non-empty. V of R is non-empty. Sorry. Yeah, so this proposition can only be true if we restrict attention to the cases which have a local solution, because if there's no local solution, then the measure could equal 0. Proposition 1 and 2. Proof, well, if you assume these propositions, it's not so hard. So if V of Q is empty, then NV of B should certainly equal 0. There should be no points of small height. So either NV of B alpha W is at most eta times B over A, or the difference is greater than eta times B over A, and the probability of each event goes to 0. Each event in the locally soluble case So does anyone have any further questions about these statements or this short proof? So this is this will be the guide for the remainder of our two talks. We're going to prove, I'll prove proposition 2, and Pierre will prove proposition 1. Or at least sketch, I'll sketch a proof, and Pierre will sketch a proof. Proposition 2.
So in proposition 1, you say that eta is a function of A, and in proposition 2, we have A which is a function of eta.
Oh, I didn't say that, I don't say A is a function of eta, I'm saying that A is going to be sufficiently large with respect to eta. So you could also say that eta is not too small with respect to A. It's going to be, so we are going to verify that there exists A, B, W, and eta satisfying all the equations. I'm not going to verify it in this talk because it would be very boring, but you'll find out more about this over time. So in fact, what we'd like to do in this proposition is we're going to try to get rid of A and B as soon as possible. So we've expressed this counting function so it's very close to the count of irrational points, like it's a sum over these primitive vectors. And we're going to replace it with a counting function that's more local and that doesn't involve B. So step 1, replace B with a product of local terms. So we're going to have a local term at the non-Archimedean places, which is going to count the number of local solutions. Replace NV of B alpha W. And then we'll have a local term at the Archimedean places, which will be this. For here, we take the non-Archimedean part of our criterion, and we view it as a criterion on Rn plus 1, and we take some volume. And then here, we take, for this, we take the non-Archimedean part, which is that year be a solution mod W, and we take some counting measure. So the step 1 is we want to show n v of b alpha w is like some constant times sigma of fv w times tau of fv w, as long as A is sufficiently large with respect to alpha, as B is sufficiently large with respect to alpha times W. And this, what one can do in the definition, in a standard argument for counting lattice points in some region satisfying some congruence conditions. And so we can sort of now ignore B and focus on these two definitions. And the second condition that we want to know as A is sufficiently large with respect to alpha times W, we can the proportion of hypersurfaces in VDN of A, where sigma of FV W tau of FV W is greater than eta, divided by cardinality of VDN of A. This proportion will approximately be the proportion of like hypersurfaces defined over the Adels, or the proportion of basically you choose a random p-adic hypersurface and a random real hypersurface, a p-adic for each p, where sigma of FV W times tau of FV W is greater than eta. Or I guess the measure now for like the uniform measure on the Adels. So the proportion that satisfies this is we can treat the p-adic part and the real part as independent. And this, again, follows from some lattice point counting argument, where now we view the set of all hypersurfaces. We view this as a lattice. And so we're basically trying to localize our problem as much as possible. So we replaced our counting measure with the product of local terms, because sigma itself factorizes. And then we replaced our distribution with a product of local distributions. So the only thing that's not local is this condition, that the local hypersurface, the probability is non-zero. So then step 3, we're going to get rid of that. So is to observe that it is sufficient to prove for some delta is greater than 0 that the expectation over hypersurfaces over adelic hypersurfaces, or tuples of a random p-adic hypersurface and a real hypersurface of the function, which is 0 if v of qp is empty or v of r is empty, and is this product of fvw to the minus delta times out fvw to the minus delta, this expectation is bounded. So what we're doing, we want to detect this event when the product is small, but it's locally soluble. Whenever the product is small, the product of the power minus delta is large. And so then to get this probability to go to 0, as eta goes to 0, all we need is some kind of uniform bound for this expectation. And because this expectation factors itself as a product over product over primes p of the expectation v in Pn of qp of sigma of fv p to the vp of w. Oh, this is alpha. So the reason that we raise it to the power minus delta, rather than any other way to detect that it's small, is this term to the power minus delta will then factorize as a product. And because we already ensured that these local terms are independent at different primes p and at infinity, the expectation will factorize as well. And so what we now need to do is to control the expectation at each prime p of the function which is 0 if the local set is empty, and otherwise is a negative power of the local density. And then if we have a bound, it suffices to bound these local expectations. By local bounds that factorize whose product converges. So yeah, you can think of what we're doing. So if you write this as a product over primes p, or even better, if you think about not bad. If you think about the true local density, it's a product over all primes p. There's really two possible reasons that it could be small. The first reason is if for some particular prime p, the local measure is very small. And the other reason is if for many primes p, the local measure is a little bit smaller than 1, or a little bit smaller than its average value. And so this expectation of the power minus delta lets us rule out both those possibilities simultaneously using only local bounds at the primes p. Okay, so it's this one then. I'm not good at this at all. So this one has to go down. And yeah, let's go. So I have a little bit of time left to say something about the local values. Step 4, we need to estimate the expectation of the function, which is 0 if v of qp is empty, and is equal to phi of p to the vp w over p to the n vp of w. The cardinality of v over z mod p to the vp of w minus delta. So we would estimate this kind of expectation of this inverse power of the local counting function. And so because v of qp is not empty, we know this local counting function is at least 1. So that gives us some kind of upper bound on this power, but it's not at all uniform in W. So to get a uniform bound in W, there's 2 steps. There's some steps. So the first thing we do is we evaluate the first and second moments. Of the number of points of z mod p to the k. So this is an exercise. We'll actually be doing a much more difficult version of this in the next talk. Here is relatively straightforward to evaluate the first and second moments of the number of points on a random hypersurface. So using this, we can estimate any quadratic polynomial. Of this quantity. And so, but we don't want to estimate a quadratic polynomial. We want to estimate the quantity raised to the power minus delta. So this minus delta function has a pole at 0. So we can take, usually, for instance, if v is smooth and p is relatively large, the number of points will be very close to its average value. So we can take a quadratic upper bound for this some pole. We take a quadratic upper bound. Bound for x to the minus delta away from 0. Sorry for the squeaks. So this function has a pole, but away from the pole, we can upper bound it by a quadratic thing. And then we know the first and second moments, so we can upper bound the expectation. And so to deal with the pole, so for most of the problem, most of estimating this expectation, we don't really need to use the fact that we're locally soluble. Like adding this local solubility condition doesn't make it any easier to evaluate these two moments. It makes it harder. But to handle the pole, we do kind of need to use the fact that we're locally soluble. And so to deal with the pole, we use the local solution. And then we also use Hensel's lemma. So Hensel's lemma will tell you, is a way to tell you when you have a p-adic point, you have a mod p point, and then you can lift that to many other p-adic points. So Hensel's lemma shows you that if x is in V of QP, and the derivative of f at x is not 0 mod p, then the number of solutions is at least the number of lifts of this point, which is p to the k to the n minus 1. And in or p to the k minus 1 to the n. And then in general, you can show that the number of solutions. So this works great as a lower bound if there's any point that's non-singular, mod p. But there might not be any non-singular points mod p. And so what you have to do is you have some lower bound in terms of the derivative. So there's a generalization that says the number of mod p to the k solutions is, has some lower bound depending on the p-adic valuation of the derivative, minus the vp of the gradient of f at x. Something like this. So as long as your p-adic derivative at a point is not 0, you have some lower bound for the number of solutions at that point that is uniform in W, which comes from a Hensel's lemma type argument, a p-adic lifting argument. So what remains to bound the tail is we need to bound the probability that there is a p-adic solution but all solutions have the p-adic valuation of their derivative greater than some constant c. So if we have any p-adic solution where the derivative is small, we can lift it and get many solutions, and we can get a lower bound. So we need to rule out the case when all our p-adic solutions have small derivatives. But the way to do that is to use, I guess, a syllogism or something to just bound the probability that there is a p-adic solution x with derivative with the p-adic valuation of its derivative greater than c. So if there is a solution and all solutions have a big p-adic derivative, then there is a solution with a big p-adic derivative. And then it's sufficient to bound this. We bound the number, the expected number of x, where x is a p-adic solution. X is in V of QP. and the derivative is greater than c. And then this is, you can bound by an exchange of summation argument, and it gives you a bound that's good enough to bound the tail, and then it multiplies out, and you get a good bound for the expectation, which then gives you a good enough bound for the probability that the local density, the product of local densities is small. All right, thank you.
Any questions, please?
Why n at least d plus 2?
You'll have to wait for the next talk to find out.
And then a second question. Sorry.
I'm good at shouting.
Okay.
Okay, maybe you want to
So I was wondering about complete intersections. Is there a chance?
I think the method should work for complete intersections, right? Like it should just be, there should just be more. A lot of things that we do, probably especially in Pierre's talk, would get a lot more laborious for complete intersections. But I don't see any reason that it should fail, right? There should, for some, maybe the sum of the degrees should be at least n minus 2, or the sum of the degree, or should be most n minus 2, or the sum of the degrees plus 2 should be most n, something like that. Something like that, I think it should work. Because, yeah, I mean, I guess I'd have to think not just about derivatives, but about like Jacobian matrices or something. Like everything would just get much more complicated, but there's no fundamental obstruction that I'm aware of.
Well, it's a question of the same style. What about integral points? Representation of an integer as a sum of 4 cubes, for instance.
Integer, so, well, yeah, I think we can also do something about, we can do something about integer points. So everything is based on the assumption that a polynomial is homogeneous, but if you don't work with a homogeneous polynomial. So one subtlety of the integer point case is there are more, for polynomials, there's one really natural, for homogeneous polynomials, there's one really natural height function of homogeneous polynomials. And so there's one very clear notion of density, or at least one very clear notion of density 0. But for polynomials that are not homogeneous, there's different natural notions of height function. And it's not obvious which one you would take. Maybe you try to improve the result for more than one notion of a height function to make things maximally general. But yeah, I mean, it would require more work. But I mean, the method relies on counting integer solutions to the homogeneous equation that are primitive. So it certainly suggests the same method should work for integer points.
I also have a question. Is this set of polynomials satisfying the Hasse principle? Does it have distribution properties? Like, can you approximate them periodically, or?
Yeah. So if so you're asking if this set has distribution properties, you'd want to know that for any like p-adic congruence condition, you can find a polynomial satisfying the Hasse principle. Yeah. So our method will work if you're adding additional p-adic congruence conditions. The same method should work. Well, if you just want to know a polynomial satisfying the Hasse principle, then there's a trick, because you can just make it not locally soluble, and then it'll automatically satisfy the Hasse principle. So, but yeah, so the method will produce polynomials which satisfy the Hasse principle because they have a rational point in any congruence class, unless your congruence condition forces there to be no rational points. So it's very robust in that sense.
Any other questions? Okay, if not, let's thank the speaker again.